कि we've got अच्छा ये हम पढ़े थे कि we've got factors that affect the rate of reaction. ठीक है, ये सारा हमने पढ़ा था कि कौन-कौन से factors हैं that affect the rate of a reaction. So one of them was temperature. कि I told you कि मैंने कहा था कि rate of reaction है कि particles are bumping into each other, they're colliding with each other. So I told you कि it depends on two things. One is the frequency with which they collide, yani how many times they collide with each other, and the other one is how effective is the collision. Like कितने जोर से, how forcefully do they collide? ठीक है, or how successful is the collision? Okay, you might have that the particles are bumping into each other a lot, like they bump into each other 1,000 times a second. लेकिन ये हो सकता है कि even after 1,000 collisions, there is no successful reaction. So it also has to be an effective collision that leads to a reaction. ठीक है, for example, आप wood का piece है, उसको आप मार रहे हो. It doesn't really matter कि आप कितनी दफा मार रहे हो, आप उसको तोड़ने की कोशिश कर रहे हो, तो how strongly do you hit it? ठीक है. So that is kind of something that happens when reactions happen. I told you जब हम catalyst पढ़े थे, I told you कि what happens during reactions is कि the molecules like H2 and Cl2 molecules, they bump, they collide, and when they collide, the old bonds are broken. Just HH or ClCl, they're bonded together. So when they bump into each other and they collide, there's a small collision and the molecules, they break apart. The Cl atoms break apart, the H atoms break apart, and then the H and Cl might get together to form HCl. Something new would be formed, something, they would rearrange themselves, and something new would be formed. So वो इसी तरह से wood से आपने कोई चीज बनानी है, the first thing you have to do is you have to cut the wood, ठीक है, you have to break it into pieces, and then you sort of join them again in different ways. So chemical reactions are kind of the same. Okay, the previous molecules are going to bump into each other, the old bonds are going to break, and then something new would be formed. Okay, they would rearrange themselves. So the thing is that the collision has to be effective, it has to be forceful enough so that the old bonds get broken and then new bonds are formed. Anyway, so we did these 5 factors. Okay, I told you that temperature increases the kinetic energy of the particles, they start moving faster. When they start traveling faster, you get more frequent collisions, they bump into each other a lot more. And they also have effective collisions because now the particles are more energetic. So they bump into each other with a lot more force. So you get more successful collisions as well. Second was pressure. Pressure, I told you, okay, when you increase pressure, what you're doing is you're basically compressing it. So when you compress them together, so what happens is that the particles are closer together, so you get more frequent collisions, which leads to a faster reaction. The effectiveness or the successfulness of the collision remains the same because you're not giving them energy this time. So the collisions are not becoming more energetic or more forceful. The only thing you're doing is you've just brought them together closer, so they will bump into each other a lot more. Achha, you had this concentration thing. Solutions ke andar usually hota hai कि when it's more concentrated, you got more particles per unit volume. That means they would be closer together and you'll get more frequent collisions. And then I talked about surface area. Okay, you've got a large piece or a large lump would always have a slow reaction. Why? Because it's always going to have a slow reaction. Why? Because ye jo andar wale particles are the ones that are sitting inside, they're not able to react. The outer surface is able to react, but the middle ones are not able to react. If you break it into pieces, tiny pieces in powdered form, then all the particles would be able to take part in the reaction and you will get a faster reaction. You'll get more frequent collisions this way. And the very last one was a catalyst. I told you that catalyst, what it does is it lowers the activation energy and leads to more effective collisions. The frequency of collisions kind of remains the same. So I told you, okay, what a catalyst does is, okay, whenever you have a reaction, you have to break the old bonds. So what a catalyst does is it kind of makes it easier for you to break the old bonds, because once the old bonds are broken easily, then the reaction would speed up, because that is what is preventing the reaction from happening. कि अगर पुराने bonds बहुत ही ज़्यादा strong होंगे, ठीक है, and they won't break, so that would not lead to a reaction because it would be very hard to break this bond. So what a catalyst does is that at the very start, you need to, some energy is needed to break the old bonds. So what a catalyst does is it kind of makes it easier to break the bonds. This nitrogen ka molecule, the triple bond in nitrogen is really strong. So catalyst makes it easy to break your old bonds. So it lowers the activation energy. It lowers the amount of energy that is needed to start a reaction. It's like you striking a match. So a match lights up when you strike it. The reason you have to give it energy is so that the old bonds are broken and then new bonds would be formed. So every reaction, for it to start, like if you want to burn paper, you have to give it energy first. And the main reason is that you have to get rid of the old bonds. You have to break them. And then it can react with the air and form new bonds. So the point is every reaction needs some activation energy. क्योंकि पुराने bonds तोड़ने, they need some activation energy so that the old bonds are broken. If it's really hard to break old bonds, the reaction would be slow. So if activation energy is very high, which basically means very hard to break old bonds. So if it's very hard or difficult to break old bonds, what's the एक second में share करो link. So the thing is, if activation is very high, very hard to break old bonds, then reaction is going to be slow. For example, why is it so hard to break a large piece of wood? Sorry, why is it so difficult to burn a large piece of wood? Because the bonds are not broken. If you break the large piece of wood into smaller, tinier pieces, it's much easier to burn it because you've done half the job. You've broken the old bonds. So the reaction is going to be very slow and vice versa. Okay, is this point clear to everyone?
Yes, sir.
ठीक है. और फिर ये कि हमजा ये टॉपिक के एंड पे ना we'll do past papers. Now, so I'm just going to go back, just a quick recap. ये वाला तो कर लिया. Remember what was rate of reaction? Rate of reaction was any change with respect to time, like how fast something changes in a reaction. And I told you it could be any change, bubbles forming, dissolving, color, mass. So if the color changes very quickly, it's a fast reaction. If it takes a long time, it's a slow reaction. So I told you that when you talk about rate of reaction, you talk about, you always plot a change that's happening with respect to time. And that change could be anything. It could be a color change. For example, in this reaction, it could be the volume of H2 gas that's forming, or the mass of Mg because it's going to dissolve. So its mass would decrease over time. So you can plot the mass with respect to time. So the steeper is the gradient of the change, the faster is the reaction. So remember this thing as well, that whenever you plot the graph, if the graph is really steep, that means it's a fast reaction. So vice versa, if the graph is not that steep, that means it's taking a long time. That means it's a slow reaction. So it could be any change. For example, over here, I'm plotting the volume of H2 gas that's being produced. So initially you had zero volume, and then it started to increase, and then it became constant. That means the reaction has, this point, if it becomes constant, that indicates that reaction has stopped because the volume of H2 is not changing. That means whatever had to be produced is already produced. So if volume of H2 is being produced at a very fast rate, like the graph is really steep, then that means faster reaction. So anyway, so we're almost kind of done with rate of reaction. There are two processes that we have to study. Then we'll do past papers on this. Remember, we did equilibrium and we did rate, and I told you that both were kind of interlinked. I said we did equilibrium, Le-Chatelier principle, and we did the rate of reaction and the factors that affect the rate of reaction. Now, there are two processes that you have to remember, just like your previously extraction of metals. We have two processes. There are two processes over here as well. One of them is known as the Haber process. This is something that has to be memorized. It's got to do with the manufacture of ammonia. Now ammonia is a pretty important chemical industrially. You use it for explosives. You use it for nitric acid formation. You use it for fertilizer. That's the number one thing. So I'll just find other uses. You just need to know two uses. That's it. So for example, there's this chart that's so the number one is making fertilizers. Making explosives. That's another one. And then you've got all the other things as well. So it's a chemical that's very important in a lot of industries. So ammonia is produced or manufactured in very large amounts. So we use it for manufacture of so just writing the uses just a second. Just remember two uses, that would be enough. One is fertilizers. So fertilizers are frequently used in bulk quantity. It's a huge industry. Fertilizer industry is a big industry. The whole world depends on plants and crops. So this is a pretty big industry manufacturing wise. So fertilizers you make ammonium salts from it. The other one is for making nitric acid. You make explosives from it. So a really important chemical compound. So you need to know the process of manufacturing ammonia. So it's a simple reaction. You've got N2 reacting with hydrogen gas, and together they produce ammonia gas. So they together produce ammonia gas. That's it. That's the whole reaction. The enthalpy change of this reaction is exothermic. It's an exothermic reaction. It is negative, which basically indicates that the forward reaction is the one that's exothermic. Like making or manufacturing ammonia is an exothermic process. It releases energy. The other one, the opposite one, is going to be endothermic. But anyways, we're supposed to make ammonia. I want the reaction to go in the forward direction. The conditions for this reaction are you need a catalyst, which is in the form of iron. So remember the conditions. The temperature that's used for this reaction is 450. And there's one other thing, and that's pressure. The pressure that's used for this reaction is 200 atmospheres. So the whole, so just remember this conditions. The other thing that they're going to ask you about is where do you get nitrogen? Where do you get hydrogen? So what's the source of the raw materials? So what's the source? Where do you get this nitrogen and hydrogen? As a number one, can anyone tell me where do you get nitrogen? What's the source for nitrogen? Where do you get it? Anyone, any idea? क्या होगा इसका? But which place is full of nitrogen? Just anyone, just a random guess. What's any idea?
Air.
Okay, that's air. So remember, nitrogen, you get it from air. You get it from fractional distillation of liquid air. You liquefy the air, and then nitrogen has a particular boiling point. So you boil it and you collect it in some container. So fractional distillation of liquid air. Because 78% of it is nitrogen. So air is mostly nitrogen. And then you have another one, which is where you get hydrogen. So hydrogen, remember, is you get it from electrolysis of, I mean, that is secondary. The first source is cracking of oil that you'll study much later on. Okay, so just remember it's cracking of oil or electrolysis of water. Electrolysis is kind of expensive, so usually we just depend on the first one, that is cracking of oil. You get it from oil that you obtain from the Earth's crust. You extract hydrogen from that. Okay, the process will be discussed later on in organic chemistry. I said, now the thing is, you have this Haber process. We know what the source is. Just a little random diagram, and that is that a little bit more information about this. So here's so let's say there's this container where the reaction is happening, and you're adding. So anyway, so what you're doing is, so what you're doing is you're adding nitrogen gas, and you're also adding hydrogen gas into this container. Okay, that's what you're doing. And ammonia comes out at the other end. Okay, so there's ammonia gas. The reaction happens, and you get ammonia gas at the other end. And then the unreacted, what happens is that the unreacted gases are recycled back. So the unreacted gases are recycled back into the container. Let's just a second. So I mean that's about it. So the unreacted gases are recycled back. I said the thing with this reaction is that this reaction has a terribly low yield. So ammonia has a really low yield, around 10 to 20%. Okay, so it's a pretty bad yield. What yield means is that most of the nitrogen, remember, it's a reversible reaction. Okay, the problem with reversible reactions is that as soon as ammonia is produced, the reverse reaction would also start. That means some of the ammonia will get converted back into N2NH2. So not all the N2NH2 are able to completely react to produce ammonia gas. Because if I have 10 molecules and I'm expecting 10 molecules of ammonia to form, some of them would start the reverse reaction. They would turn back into N2NH2. So the amount of ammonia that is produced is actually quite less, because most of it gets converted back into N2NH2. So it's a reversible reaction. It's like water vapors, the reaction with water vapors. That when we were discussing equilibrium, Okay, we did discuss it somewhere over here. So when we were discussing equilibrium, I told you that why doesn't water evaporate in a closed bottle? And the reason is that it is evaporating constantly. But the thing is that some of the water vapors, like as soon as they're formed, they start condensing back again. So the thing is, if 10 molecules evaporate and 10 molecules condense back, the net result is the amount of water vapor kind of remains constant. So which is why all the water vapor is not able to evaporate, because it's constantly condensing back again. So something similar kind of happens with this one. Okay, you're not able to, where's the reaction? Just a second. So something similar, इसको एक से हटा ही देते हैं. अच्छा, so something similar happens, and the unreacted, something similar happens. Ammonia is extracted or removed from the container because ammonia has a very high boiling point, so it liquefies quickly. So ammonia is cooled, and liquefied, and removed from the container. So you have to constantly remove the ammonia from the container. कि अगर इस container में ना N2 reacted and a little bit of ammonia is produced, you're going to constantly try and remove it by liquefying it. It's got a high boiling point, so it liquefies quickly. N2 and H2 have very low boiling points, so they don't usually liquefy that easily. And the unreacted nitrogen and hydrogen gases are constantly fed back into the system. So is this point clear about the low yield? Is this clear, everyone?
Yes.
Yes, sir.
ठीक है.
Yes, sir.
अच्छा, so that's it. So it's not a reaction which produces a lot of ammonia. ठीक है, just remember that. Now, one very important thing about this reaction, we studied most of it. The sources of the raw material, we've studied the uses of ammonia, we've studied the conditions for the manufacture of ammonia in the Haber process. What needs to be studied now is, why do you use these conditions? Okay, so there's a separate small question that usually comes, that you should justify the conditions that are used in the Haber process. But why did you use those conditions? नहीं, सुभान की वो एविडेंस है उसकी ऑप्टेड आउट का?
जी सर, वो ब्रिटिश काउंसिल कॉल की थी, मैं वेबसाइट उन्होंने दी थी, उस पर फिर इंफॉर्मेशन डाल के फिर
नहीं तो उसमें
एग्जेम्पशन
तो उसकी
किया था।
एविडेंस है ना?
एविडेंस आज सच में पास तो नहीं है कोई।
नहीं, ईमेल वगैरह कोई नहीं आई उसकी, या कोई
ईमेल आई है
तो क्या तुमने एग्जेम्प्ट किया ना, मतलब उसकी ईमेल आई होगी ना कंफर्मेशन?
जी।
तो वो उनको दोबारा शेयर करो, उनसे कहो कि ये क्या है,
ओके।
या उनका कोई प्रोसेस होगा शायद, वो उन्होंने सबको भेज दिया होगा, बस वो जिनको एग्जेम्प्ट किया हुआ दे नॉट सपोज
वो
टू।
उन्होंने कहा था कि अगर आप एग्जेम्प्ट कर रहे हैं तो यू आर नॉट सपोज्ड टू गिव एटीपी, लेकिन एज अ कंपोनेंट उन्होंने भेज दिया तो मुझे समझ नहीं आ रहा।
नहीं, वो उनसे पूछ लो कि अगर तो एग्जेम्प्ट किया हुआ वो भी एविडेंस भी है, तो फिर तो एग्जेम्प्टेड है ना, लेकिन वो उनसे कंफर्म कर लो कि क्या करना है।
ओके।
ठीक है, अच्छा चलिए ये वाला, you have to justify the conditions that are used in the Haber process. So one by one, remember it's an equilibrium reaction, so the reason they're looking for justification is related to equilibrium and rate. Like the first part is, what's wrong with using temperature greater than 450? So what's the pros and cons? Why did you use 450? Why not a higher temperature? So I'm just make it temperature is equal to 450. Why do we use temperature 450? So what's wrong with a higher temperature? Why not a higher temperature? Why not 1000 degrees centigrade? So first thing, I'm going to comment ठीक है विनायक? अच्छा, so what I'm going to do is I'm going to comment on the higher temperature first. Remember, according to equilibrium, higher temperature favors the endothermic reaction. So it favors the endothermic reaction. And in this case, the endothermic, remember, this is the rule Lee-Shatler principle that we studied when we were doing equilibrium. I told you that higher temperatures always favors the endothermic reaction, which is the backward reaction in this case. Is this clear?
Yes, sir.
तो अगर तो backward reaction है, that means फिर तो ammonia कम बनेगी. There's going to be less ammonia formed क्योंकि we don't want the backward reaction to happen. So yield would decrease. Yield would decrease and less ammonia would be formed. Okay, so remember we did this in Lee-Shatler principle equilibrium that I told you higher temperature always favors endothermic reaction. So which is why we're not increasing the temperature greater than 450, because if you increase the temperature, backward reaction would be favored and the yield would decrease and less ammonia would be formed. So is this clear?
Yes, sir.
So why don't you, so the next thing is why do you not use a lower temperature? Because according to equilibrium, the lower temperature favors the exothermic reaction. It favors the exothermic reaction. So the exothermic over here is the forward reaction. So that's kind of a good thing. So the exothermic reaction is the forward reaction. So that means the yield would increase. So the yield is going to increase. So that's kind of a good thing. But what's the problem? Why don't you lower the temperature? Because remember, in the rate of reaction, we studied what happens if you, where's the temperature? What happens if you lower temperature? The reaction slows down. Higher temperature, the reaction is fast. Lower temperature, the reaction slows down because the molecules have lesser kinetic energy. So they're not going to travel very fast and they're not going to bump into each other a lot more. So lower temperature, the problem with the lower temperature is not about the yield. So at lower temperature, it's going to favor the forward reaction. You're going to get more ammonia, but the only thing is you're going to get ammonia after a longer time. So, but the rate of reaction slows down. तो मतलब फायदा नहीं होगा कि you're getting more ammonia, but you're getting it after, let's say, 15 days. So why not get less ammonia, but like in 10 minutes? So you have to take into account the time that's taken for the reaction to happen. So the problem with lower temperature is there's going to be more yield, more ammonia would be produced, but it's just going to take a much longer time because at a lower temperature, the rate of the reaction is going to be pretty slow. So is this clear? Okay, 450 is a compromise. A higher temperature than 450 decreases the yield of ammonia because the endothermic reaction is favored, and a lower temperature, it does increase the yield of ammonia, but just takes a longer time. So this is kind of a compromise. Is this clear?
Yes, sir.
Yes, sir.
ठीक है, बाकी Hamza, is this clear? Subhan, clear है?
Yes, sir.
Yes, sir.
Ajay, so next one, pressure क्या use? We were using pressure as 200 atmospheres. So the first question is, why don't you use a higher pressure, sorry. So what's wrong with using a higher pressure? So it's a pretty good thing because at higher pressures, the particles are pressure. This one. So at higher pressure, when you compress it, the particles are closer together, so they bump into each other a lot more and you get a faster reaction. So that's kind of a good thing. Okay, so I mean, we should use a higher pressure, greater pressure than 200 atmosphere. That's good. Higher pressure. What do you get? Particles are closer together. ठीक है, ये बात clear है?
Yes, sir.
So you get a faster reaction. Plus another thing, एक तो ये point हो गया. There's another advantage of using a higher pressure. I mean, instead of using 200 atmospheres, you should use 500 or 1000 atmospheres. Another thing is equilibrium. Higher pressure equilibrium favors less gas mole side. So less gas mole side is going to be favored. Which side is the less gas mole side in this case? It's the forward side. The forward side is less gas, the backward side is the more gas mole side. Because there are 4 molecules, over there are 2 molecules. So if the reaction goes forward, the less gas mole side is favored. So in this case, remember Le-Chatelier principle, pressure ka ye tha ki if you increase pressure, what you're doing is you're compressing it. So less gas would be formed. If you decrease pressure, you're expanding it. So more gas is going to be formed. Now, in this case, you're increasing pressure, you're compressing it. So that means less gas would be formed. So more forward reaction. So there's going to be more forward reaction. Is that also clear?
Yes, sir.
And you are going to have a greater yield. Is that clear? I'm not clear. SN, is this clear? What's that?
Yes, sir.
अच्छा, अब ये कि you're going to have a greater yield. तो दोनों चीजें अच्छी हैं, मतलब you get more ammonia. So can anyone point out what's wrong with using a higher pressure? Like why you should not use a higher pressure? एक तो वो closer together, you get a faster reaction. You also get more ammonia as well because the equilibrium favors the less gas mole side. So the more product would be formed. The drawback of using a higher pressure is that it's going to be extremely expensive. Because remember, higher pressure maintain karna, that's kind of difficult because you would have to compress things. ठीक है, a lot of मतलब जैसा आपका मतलब higher pressure can only be obtained यहाँ पे. How are we obtaining the higher pressure? I mean, you had to sort of push this down so that the pressure increases. So there has to be a constant force. Compressors वगैरह apply करने पड़ेंगे. You have to bring it to high pressure. Plus, high pressure things are unsafe because the whole thing could explode. Like if you compress it too much, it could explode. So it's also unsafe. कभी high pressure पे चीजें देखी, a lot of previously you had these compressed natural gas tanks in cars, and they had a habit of exploding. So higher pressure का issue ये भी है कि they would lead to explosion. So you would have to make it out of a much thicker material ताकि it doesn't explode. पूरी जो factory होगी ना, the pipes etc., they would have to be made from a much thicker material. So that's one of the problems with using a higher pressure. So the drawback is higher pressure is more expensive. It's expensive and costly, and you can also add it's dangerous as well. So remember, हमने factory के अंदर produce करना, there would be people working around, so you don't want things to be at such high pressures. So 200 atmospheres, that's sufficient. No need to go till 10,000 atmospheres or 20,000 atmospheres. If things are working fine at 200 atmospheres, so why don't save your cost? It's better to have an even higher pressure, but it's also important to save your cost. So is this clear? Clear है
जी
साहब?
सर.
अच्छा,
जी सर.
और इधर ही ना मैं लोअर प्रेशर का लिख देता हूँ कि लोअर प्रेशर का वो सारा लोअर प्रेशर का नुकसान ही नुकसान है, क्योंकि the particles are further away and you get a slower reaction. Plus equilibrium favors the more gas mole side, जो कि ऊपर backward थी. तो problem with lower pressure is why you should not use a lower pressure. Lower pressure decreases equilibrium yield. So it decreases equilibrium yield and favors the more gas mole side, which is backward. So which is backward reaction. And also you get a slower reaction as particles are far apart. Far apart. तो ये justifications पता होनी चाहिए. Temperature ज़्यादा क्यों नहीं किया, कम क्यों नहीं किया, pressure. What's wrong with high pressure? Everything is good with high pressure except for the cost. So you have to save your cost. Why not a lower pressure? Because everything is bad about a lower pressure. It decreases the equilibrium yield, favors the more gas mole side, which is the wrong side in this case, backward, and also gets also you get a slower reaction as particles are far apart. Okay, is this clear?
जी सर.
Yes, sir.
बस ठीक है, चलो ठीक है, ये कल कंटिन्यू करते हैं. ठीक है, ये हो गया हमारा कंप्लीट. इसमें बस एक मैं एक पॉइंट बस ऐड कर दूं कि कैटलिस्ट को जस्टिफाई करना दैट्स इजी. What's the justification of using a catalyst? Because you get a faster reaction, so that's a good thing. You get a faster reaction at a lower temperature. क्योंकि catalyst activation energy को कम कर देता है. So that's kind of a good thing. Catalyst का फायदा ही फायदा है. ठीक है, वो हमने डिटेल में पहले ही पढ़ा है कि it lowers the activation energy and speeds up the reaction. So that's kind of a good thing. So उसको justify करने की जरूरत ही नहीं है. मतलब वो वैसे ही आपको ऐड करना ही चाहिए हर दफा if that's an option. चलिए ठीक है, let's continue next time. ठीक है, okay everyone. Take care, Allah Hafiz.
Yeah, sir.
अल्लाह हाफिज़ सर.